So tonight, it's our honor to have Dr. Jordi Casanova from Regis University. Dr. Casanova earned his Ph.D. from the Polytechnic University of Catalonia in Barcelona and is assistant professor at Regis University. Previously, he has worked at North Carolina State University and Oak Ridge National Laboratories as a postdoc researcher. Here in Colorado, he is taught at the Colorado Community College System and at the Metropolitan State University of Denver. He is a theoretical astrophysicist interested in deciphering how stars explode and die. Please welcome Dr. Jordi Casanova.
All right. Good evening, everyone. Thank you so much for inviting me to give this talk today at the Denver Astronomical Society meeting. Today, I'm going to talk about the splendor of the Coronae Borealis. Let me close this. Okay, perfect. Now I see the slides on my screen. I'm going to talk about the Coronae Borealis. We know that the Coronae Borealis is also known as the blaze star, and we know that the blaze star, or the Coronae Borealis, is a nova explosion, and we know that nova explosions occur in stellar binary systems. This is what the image on the left is showing. The image on the right is showing the location of the Coronae Borealis in the sky. We also know that the Coronae Borealis is a recurrent nova and explodes every 80 years. Perhaps it is exploding right now as we speak. That would be wonderful. I don't think that's going to happen though, but in this talk, I'm going to summarize the current status of this unique system. Stellar nova means new star. This is in Latin. When I was invited to present at the spring banquet back in, I believe that was 2024, I extensively talked about classical nova explosions, which is the topic of my research. I'm not going to repeat the same talk, but because the Coronae Borealis is indeed a nova explosion, I think it's a good idea that we start by understanding what a nova explosion is. This is a video that shows the scenario for a classical nova explosion. So we have two stars. The star in the center is a white dwarf and accretes material from the companion. This material forms an accretion disk and falls on top of the surface, and that triggers what we call a nova explosion. So then if we aim our telescopes to that specific system, we can see this new bright source in the sky, which indeed corresponds to the nova explosion. This is the famous image of Nova Cygni 1992 that was taken by the Hubble Space Telescope. And this is a wonderful image because especially the one on the right, we can see this, it's not a ring of fire, but this is representing the ejected material from the system. And we can still see the system or the binary system in the center, which means that the stars survived the explosion. This is a nova that was discovered by the amateur astronomer Peter Collins from Boulder, Colorado. And maybe we can say that this is our Colorado nova. At the time of the explosion, the magnitude was around 7.2. It was not that bright or as bright as the Coronae Borealis will be. So this is the scenario for the classical nova scenario. We have a binary system. I'm going to use the laser pointer. We have one of the stars, the principal star is a white dwarf. The typical composition of a white dwarf could be either carbon-oxygen or oxygen-neon in the core of the white dwarf. Then we have the companion star. It's usually a low-mass main sequence star. Sometimes it might be a red giant, and there are some other possibilities for the nova scenario. Because the gravitational field of the white dwarf is very strong, it pulls material from the companion, and this material flows through the inner Lagrangian point. This is this point here in this 8 or infinity figure. This material flows or spirals towards the white dwarf due to conservation of angular momentum. It forms an accretion disk surrounding the star, and just a portion of this material ends up falling on the surface of the star, the white dwarf, and that triggers the explosion. So what are some properties of classical novae? So they usually have very short orbital periods, usually less than 24 hours. That would be 1 day. These are typical mass transfer rates. They are really small. They can be as much as 10 to the negative ninth solar masses per year. Novae or classical novae can accrete for a long time. For instance, they can accrete material on top of the white dwarf for about 10,000 years or 100,000 years. So the total mass that accumulates or piles up on top of the white dwarf could be as much as 10 to the negative fourth solar masses. So this is the mass of the sun divided by 10,000. So then we have that the accretion of hydrogen-rich material that comes from the companion on top of the white dwarf is going to power what we call a thermonuclear runaway. When I say hydrogen-rich material, I'm talking about solar composition or metallicity of 2%. Metallicity in astronomy is anything that is heavier than helium. All right, so we have all this accretion, we have an explosion, but why is there an explosion? Let's try to understand why we or white dwarfs will power this nova explosion. So we have all this material falling on top of the white dwarf, and this material gets compressed, it becomes partially degenerate. And this is an important point because when material is partially degenerate, that means that the temperature and the pressure are sort of disconnected. That means that I can increase the temperature without having an increase in the pressure, so there is no expansion of the accrete envelope yet. So that allows the temperature to keep increasing, and when it's around say 10 million kelvins, this is time for some nuclear reactions to take place, operate at the accreted envelope. So usually through the what we call the proton-proton chains and also the CNO cycle. Because there is, or the temperature keeps increasing, that triggers convection, and convection also plays a very important role in this system or in this scenario because now there is circulation and there are some chemical species that are produced during the outburst, and these are these guys here, nitrogen 13, oxygen 14 and 15, also fluorine 17, which will be transported to the outermost layers of the accreted envelope. So now there is circulation. When they get there, they disintegrate and they release a huge amount of energy. And this energy actually breaks degeneracy. And this is important because now pressure and temperature are connected again. So because the temperature is really high, the pressure is going to be really high, and that powers an explosion. So nova can eject as much as 10 to the negative 3 solar masses. This is the mass of the sun divided by 1,000. So this is a big chunk of mass, which is going to be ejected. And this might be the typical velocities of this ejected material, a few thousand kilometers per second. Now, this is a very important point. Whenever we go and observe nova explosions and we analyze the ejecta, we find that the ejected material usually results in what we call non-solar isotopic abundances. That means that the metallicities in the ejecta are really high, usually above 20%. So where do these metals come from? So we think that these metals actually come from inside the white dwarf. And when I say metals, I'm talking about carbons, oxygens, neons, and magnesiums. And these metals will be transported to the accrete envelope because there are some mixing processes operating at the core envelope interface. And that eventually is going to increase the metallicity of the accrete envelope, but also the like the metallicity in the ejecta. That was indeed the dissertation topic, and that was something that we published many years ago now. All right, so what can we find in the ejecta of classical novae? So novae are the second most frequent explosions in the Milky Way. We can expect at least 2 nova explosions per month, maybe around 30 explosions in a year. We have identified a few hundred nova in our galaxy. We started monitoring novae in neighbor galaxies such as the Andromeda galaxy. The last brightest nova was Nova Cygni 1975, which actually reached the magnitude of 2. And 2 is actually really bright in the sky, that means that we could see it with a naked eye. So this graph is actually showing the typical nova light curve. So this is magnitude versus, or brightness versus time. So there is usually a sudden increase of 8 to 18 magnitudes, then it reaches a maximum, and then brightness starts decreasing. How fast this decline of brightness happens defines the type of nova, slow or fast nova. What else can we find in the ejecta? So basically, nova contribute to the galactic abundances in the Milky Way. They are major sources of carbon-13, oxygen-17. I'm going to say also nitrogen-15s, lithiums, aluminum-26. Only the more massive nova can produce heavier isotopes. Also, nova are very important for gamma ray astronomy because during the explosion, there are some chemical species like these ones that I'm listing here, which will emit gamma rays. And this is perfect because we can just go observe the explosion. And if we detect gamma ray emission from this system, that's going to confirm the predictions from the thermonuclear runaway model. Nova also emit X-rays. This is because after the eruption or the explosion, not all the material will be ejected from the surface of the white dwarf. So part of this material remains on top of the white dwarf and keeps burning steadily. The temperatures are really high, and that powers what we call super soft X-rays. And this might be a perfect way to check if or whether or nova could be the progenitors of type 1a supernova, which I'm going to explain later in a few slides. So I'm not an observer. I do not go to observatories. I do not use telescopes. I do not use detectors. I'm the worst at these things, but instead I like running simulations. I have used very many supercomputers worldwide. Currently, I'm using the supercomputer Viper. This is at the University of Hull. This is in the United Kingdom. And this is through this project, Chemical Elements as Tracers of the Evolution of the Cosmos. This is a European project that provides several facilities to study nuclear astrophysics. So you can use nuclear labs, observatories, also supercomputers. So Regis University is part of this project now, and we were awarded with 0.5 millions of CPU hours of calculations. I've been modeling nova explosions, and I also started modeling what we call type 1 X-ray bursts. These will be explosions in binary systems, but instead of having a white dwarf accreting material, we have a neutron star. All right, so these are the calculations that I like running, but let's go and talk more about recurrent novae. So what are recurrent novae? So by definition, this is a nova that has recurrence times less than 100 years. So if we are lucky enough, we might see at least 2 or 3 explosions in a lifetime. So these are good examples of recurrent novae. For instance, Ares of Yuko, Scorpio, or Typixidis, or this image corresponds to Typixidis. We have identified around 11 recurrent novae in the Milky Way, not many, and Coronae Borealis will be one of them. So what are some properties of a recurrent novae? So they share the same scenario as a typical classical nova explosion, but usually they have longer orbital periods, than if we compare those to the typical classical nova scenario. Usually they accrete matter at very high rates, and the white dwarfs tend to be really massive and luminous, all right? Massive and luminous means that the temperatures and the pressures at the accreted envelope are higher, and that favors explosion. So that means that we only need a little bit of mass piling up on top of the white dwarf, and the system is already ready to explode. So that usually tends to lead to more frequent outbursts or explosions, but the explosions tend to be less energetic than those of the typical classical nova scenario. This is because usually while we accrete less fuel and we eject less mass, and the temperatures usually don't really rise that much. Now, this is the question. So are recurrent novae the progenitors of type 1a supernovae? This is a question that I've heard since I started working in this field. I'm sure that you've heard from the Chandrasekhar mass. This is the mass limit for any white dwarf. There is no white dwarf that can be more massive than 1.44 solar masses. So what happens is that if the white dwarf is a little bit more massive, the electron degeneracy from the white dwarf is not enough to counteract the force of gravity, and the star might collapse and go supernova. All right, so let's go and talk a little bit more or describe T Coronae Borealis. So T Coronae Borealis is a recurrent nova. So we can find it in the constellation of Coronae Borealis. This is here, or we can see it in this image on the right. This is an image that I took from Stellarium that represents today, September 8th at 9 p.m. So 1 hour after this talk, we can go outside and try to locate it. So this is next to Hercules. You can try to find Arcturus, which is a very bright star in the sky. All right, so T Coronae Borealis will be the circle in the image. So Coronae Borealis is also known as the Northern Crown, and it's easily seen in the Northern Hemisphere, especially in the spring and summertime. It's usually the highest in the sky around June and July, and usually goes below the horizon from our position, Denver, in winter, especially January, February. So we would expect that T Coronae Borealis should be exploding now in the summer so we could see it. This is a cool system because it's actually not so far away. It's only 1 kiloparsec away, or if you prefer, 3,000 light years away. The current magnitude at this point is 10, so that means that we'll need binoculars at least to identify it. And we have detected at least 2 eruptions in the past. There was one in 1866 that peaked 2 in magnitude. That was really, really bright. And another one in 1946 with magnitude 3. So it looks like maybe eruptions, documented eruptions in 1217 and 1787 might correspond as well to this system T Coronae Borealis. So this is T Coronae Borealis in the news. So that was the explosion in 1946. This is from the Reno Evening Gazette. New exploding star is observed locally. That was actually on Valentine's Day. So maybe many people were already looking at the sky and being carried away by the universe. And probably many people saw that new bright source in the sky corresponding to this unique system. All right, so what are some physical properties of this T Coronae Borealis system? So T Coronae Borealis is a symbiotic star. Symbiotic star means a binary system that contains a white dwarf and a red giant. So the orbital periods that we can measure are really long, 227 days. Indeed, the companion is a red giant, so that belongs to luminosity class 3, and it's an M spectral type star. That means usually a cool star, like the temperatures for this red giant might be 3,500 kelvins. All right, so the red giant is a very cold star, but because it's very large, it's actually very bright. So these are the masses that we estimate from the system. At least the white dwarf needs to be 1.3 solar masses. These are luminosities as of August 2023, 10 times the luminosity of the sun, like 10 suns shining together. And this would be an estimation for the mass accretion rates, maybe as much as 4 times 10 to the negative 8th solar masses per year. This is indeed a very large accretion rate. All right, so what can we learn from past eruptions? Do we have light curves from T Coronae Borealis? The answer is yes. So this is a study by Schaefer in 2023. And here I'm showing the light curves. This is the magnitude and this is the year. We'll see 2 different colors for data points. So the green corresponds to visible band, or say, like a filter that corresponds to yellow and green, and then blue points correspond to the blue filter or blue band. All right. So this author actually collected a lot of observations from different sources. I believe, I seem to remember that it was more than 200,000 observations, and they put all these observations together to generate these light curves. This light curve is actually fantastic. So we can see the eruption in 1866 peaking a magnitude of 2, and then the eruption in 1946. This is the explosion peaking a magnitude of around 3. There are some other features in the graph. They call it the high state, and the high state is this sudden, that's something that we can see in the blue points. This is this sudden increase of magnitude just before and after the explosion. It starts 10 years before and ends around 9 years after the explosion. And then we can see this pre-eruption dip. And this pre-eruption dip is this sudden decrease of magnitude or brightness just right before the explosion. So this is a close image. This is the magnitude, and this is the year. This is 1946. This is the explosion. And we can see here this decrease of brightness, or like around 1 magnitude less. So this is what we call, or the authors call, the pre-eruption dip. So this pre-eruption dip was discovered by Leslie Peltier, another amateur astronomer, in 1945. Now, so this is still the same light curve, and the authors here shift the explosions so that they match. So in green, we have the explosion in 1866, and then in dark green and blue, we have the explosion in 1946. And this is showing magnitude versus time since the eruption measured in days. So these two curves are shifted, and this is really amazing because probably it's not true that the curves are exact, but they are really matching here, all right? So something that we can see is this decline of at least 3 magnitudes in about 5 days. So that means that if we start at 2, 3 magnitudes less will be 5 or 6. So we'll have just a few days to go and observe the explosion with a naked eye. Otherwise, we'll need binoculars. So we'll need to go fast. All right, so this is still the same light curve. This is showing magnitude versus time since eruption in days. This is still the same data points. In green, the eruption in 1866, then dark green and blue correspond to 1946. And this is showing all the sequence. So we have, this is the principal explosion, and then we see that, well, both eruptions take about, say, like a month to go back to like what they call the quiescent state. This is this period of inactivity, which may last at least 50 days according to this data. And then we see something that they call a secondary eruption. And this is a feature that occurs in both eruptions, past eruptions in 1866 and 1946. And this is also interesting because like these structures seem to match very well. So that has to be something like indeed a very physical phenomenon on top of the white dwarf, all right, after the first explosion. All right, so this is showing the light curve of the 1946 explosion, but this is from a different source. This is from, or the data was generated from the American Association of Variable Star Observers. So this is the magnitude, this is the year, but I wanted to show this because we can see all these features. There seems to be this pre-eruption dip here, then the explosion, then this is the inactivity phase, and then this secondary explosion. All right, so everything seems to match. So we are getting all these or the same features. Now, what about these features? Are they common in other nova explosions? Well, the answer is no. So we don't really find these specific features in other explosions that we have observed. So we are gonna say that these are very peculiar from this specific system. So does that mean that we have an explanation to these features? Probably the answer is no, but we probably have some hypotheses. For instance, what about this pre-eruption dip? So this is this decline of brightness just right before the explosion. So the authors claim that that might be because of formation of dust. And we know that dust tends to obscure light, and it causes dimming, so it blocks light. And this is a plausible explanation because whenever we observe nova explosions and if we observe the ejecta, we see formation of dust. So that might be a good explanation to that. And the dust might come from previous explosions or different outflows on top of the white dwarf. We also saw this secondary maximum, like this second explosion. This is milder, but it's too energetic to be explained by, say, that the mass accretion rates are increasing. So that might be a complete second eruption. So we need to understand that this is a very massive white dwarf with like really high temperatures and pressures. So as soon as there is the first outburst, the systems continuously accretes more and more material, and because it's still very hot, that might trigger a sustained secondary eruption. And what about the high state? So this is this increase of magnitude or brightness surrounding the principal maximum 10 years before and 9 years after. So the authors claim that that might be because indeed we are increasing the mass accretion rate. So if we increase the mass accretion rate, actually we are increasing the luminosity of the system. So we are converting more gravitational energy into thermal energy. And that might be an explanation for that. As to why this increases, probably we don't know yet, all right? And you may want to say, well, this is what we understand, what we see from the past eruptions, explosions. But what is the current status of Coronae Borealis? So this is the same paper, Schaefer 2023, showing the magnitude versus the year. And this is data starting at 2005, green and blue colors. This purple line is the light curve from the 1946 explosion, which has been shifted accordingly. And this is what we've been observing. So the blue data was around 11 or 12, or between 11 and 12. And then 10 years ago, like around 2015, it started increasing. So that is actually matching what the explosion in 1946 did. So this is what the authors call the high state. So this is promising. So that's the increase in brightness signal that there's going to be an imminent explosion. Well, according to this, because that seems to follow the manual or the textbook, the authors claim that yes, so there's going to be an upcoming eruption in 2025.5 plus minus 1.5 years. So this is a range that goes between 2024 and 2027. All right, so we are still in the range. And you may want to say, well, but this was data until 2023. So what is the last data tells us? Well, so if we continue this, so this is still the same study or paper. So in 2023, so we started seeing this decline in brightness, which corresponds probably to what they call the pre-eruption dip. This is from Schaefer, but if we go to a different source, we observe the same thing. So this is magnitude versus the year. So this is 2023. So the magnitude was around 11. And now, yes, we see that in the first month, it started declining. So does this mean that this is going to explode? Probably we would like to say yes. So I was checking more data to follow this, and it looks like this stopped decreasing a little bit. It started being or like level and probably increasing a bit. So at this point, we don't know what's going to happen, but we are expecting that this is going to explode like really soon. So when it does, we are expecting to get a magnitude of 2, and this is going to be like really bright in the sky. So as bright as, for instance, Polaris. So we'll need to be ready and observe this. This is probably the current status from observations. And because I mentioned that I am not an observer, so I don't really deal with light curves, but I like running simulations, I would like to show a couple of papers that have run simulations to mimic or to model Coronae Borealis. And I'm going to show two, and I'm just going to summarize the main conclusions from these two papers. So one paper is hydrodynamic simulations of the recurrent nova Coronae Borealis. This is by the Barcelona group, and this is a very recent paper. And then this other paper, this is hydrodynamic predictions for the next outburst of Coronae Borealis. This is by the Arizona group. So both the Barcelona group and the Arizona group have been competing to model nova for many, many decades. Well, these are probably the main two groups working on nova models. So what are some theoretical predictions? So the Barcelona group basically runs a sensitivity study. They change the mass transfer rates, the mass and luminosities of the white dwarf, and they try to find or constrain these parameters so that the explosions they get mimic the explosion properties of Coronae Borealis, and especially that this is a system that can explode or recur every 80 years. So these are some of the values that they find. The mass transfer rates could be as much as 10 to the negative 7th, which is super large masses per solar year. So indeed, the mass of the white dwarf needs to be at least 130 solar masses, and these would be values for the luminosities, just to trigger that specific explosion. Some conclusions from the Arizona group, I like to highlight this. So it looks like the white dwarf is gaining mass after each eruption. I mentioned before that usually once you have the eruption, not all the material is ejected. So a portion still stays or remains on top of the white dwarf, and that makes the white dwarf be more and more massive after each explosion. So that probably means that the fate of Coronae Borealis might be going supernova, or maybe becoming a neutron star through what we call the accretion-induced collapse. What is a type 1a supernova? Well, there are different, probably, or two potential explanations. One is you have the typical classical nova scenario. So the white dwarf keeps accreting more and more mass. And when this mass overcomes the Chandrasekhar limit, 1.44 solar masses, the star collapses. All right, but when it does, the carbon inside the white dwarf ignites, and that produces a detonation which powers what we call the type 1a supernova. So this is a supernova explosion that disrupts the binary system. So this is one of the channels. There is another channel, and we think that that also might be triggered by a merger of two white dwarfs. So that might be one of the fates of Coronae Borealis. The other one is just becoming a neutron star. This is the same mechanism. So the white dwarf is so massive that starts collapsing, but it doesn't trigger ignition of or an explosion going supernova, and keeps collapsing. And then the neutron degeneracy is halting the collapse. And what we find, the remnant of this, is what we call a neutron star. So this is what we call a neutron star through accretion-induced collapse. So this might be the fate of this Coronae Borealis. And I think I'm going to stop here, and I'm going to go over the summary. So let's remember these points. So what is a recurrent nova? A recurrent nova is the typical nova explosion. That means that it's a thermonuclear explosion in a binary system. This is triggered after a very massive and luminous white dwarf accretes material from a companion star, and this usually happens at very high rates. So we know that Coronae Borealis is a recurrent nova, and it's also a symbiotic star, which means that it contains a white dwarf and a red giant. So this is a system that has been monitored since the eruptions in 1886 and also the one in 1946. So we have studied this. We have a lot of data from this system. And through this data, we just find these peculiar features in the light curve. This is the high state. This is this increase of magnitude surrounding the principal eruption. Then there is this pre-eruption dip. And then we have this secondary eruption or explosion on top of the white dwarf. So, well, it looks like the current observations and models as well, theoretical models, support the idea that this needs to explode, all right? So there has to be an imminent explosion, and we want to see this explosion. And I think the last point is also important. So that might be a good system to study whether there's a connection between nova or recurrent novae and type 1a supernova. So that would be good to go and study that specific system and see if that brings us some or shed some light into this question. And well, I think that something that we can do, or the only thing that we can do at this point, is just like, let's keep observing. And thank you so much for your time, and I'm happy to take questions. All right, thank you so much.
Hi, Jordi, it's Dina. Nice
Hello.
to see you. So to go back to the beginning, can you explain the mechanism that allows the lighter star, the white dwarf, to attract material from the bigger star? Is it a matter of difference in density or their proximity? How does the white dwarf begin stealing that material in the first place?
Yes, well, Dina, hi. Yes, that's a great question. I didn't really mention this or explain this. Basically, this is a very close binary system in proximity. So that means that because the white dwarf has this very intense gravitational field, and because the companion star is just right there, it's easy for the white dwarf to start pulling this material. So it's basically proximity. Yes? So usually these or classical novae have very short orbital periods. That means maybe like hours. So that means that the two stars orbit around each other or complete one revolution in maybe 10 hours. That means that the two stars need to be like super, super close in distance. And this is basically why this can be pulled so easily by the white dwarf.
So like the neutron-star collision, at some point, will these two attract each other enough that they will collide?
No, that's different. No, that would be a different scenario. So say that they are close enough to attract material, or that the white dwarf can pull all this material from the companion, but they are far enough not to merge. So they will start orbiting, yes, pulling material, but never becoming one thing or merging, as happens with white dwarf mergers or neutron star mergers. That would be a different scenario.
Okay, thank you very much.
Oh, thank you.
Hello? Great. Sort of a follow-on to Dina's question. You mentioned a couple different end states of the white dwarf. What is the potential end state of the red giant? Is it stay a red giant? Is it just get smaller because it's have mass pulled off it the whole time? What's its potential end state?
Yeah, basically, well, yes. So the red giant will just be a red giant. So it's not gonna change. So it takes like a lot of time to evolve from a red giant. So the fate for this red giant would be to become a white dwarf, and potentially, if that doesn't go supernova, the system will survive all the explosions, and what you will have is basically two white dwarfs, or a binary system that contains two white dwarfs. But yeah, the red giant basically will just give off all this material, but we will never see the red giant evolve during a nova explosion, because it will take millions of years to say change the state of the red giant.
Okay. I think you already answered this question, but you said the red giant could become a white dwarf. Oh, but I guess the white dwarf can never become. It'd be cool if it's this perpetuating system we go back and forth, but that's not a reality. Never mind. Sorry.
No, but this is a good question, because binary systems come in many different forms. So the typical scenario that triggers nova explosions is usually the white dwarf, that's a primary star, and then you have the companion star, which might be a main sequence star. It could be a star that is a little bit more evolved, like this, in this situation, a red giant. Or sometimes you may want to have as a companion a white dwarf or a neutron star, but that would trigger a complete complete different explosion, it could become more like a merger. All right, so that's a very specific say scenario that triggers that specific explosion. So a white dwarf, either a main sequence star or it could be a red giant. That's something that we observe.
You mentioned a secondary nova or a secondary explosion. Could that possibly be from the result of some sort of deformation of the red giant once the white dwarf explodes? And then what we're seeing is the red dwarf or the red giant bouncing back.
The red giant bouncing back.
Yeah, I'm just not sure about the fluidity of the star, you know, because you'd have the blast wave, which would technically compress.
Mm-hmm. That might be a possibility. So as far as I know, during this typical nova explosion, actually what happens is that the ejected, of course, will affect the companion star. It will not disrupt it. Maybe there is some sort of compression, and that, of course, leads to more energy into the system, and that might trigger like an increase in brightness or magnitude as we see it. That might be an explanation. The explanation that I explained, or this secondary eruption, is the explanation that the paper, the study provides for this, this increase in brightness. That might be also something that increases the brightness of the system. That might be. However, the red giant will survive even if it gets deformed or contaminated or with material from the ejected material from the white dwarf. It would still survive, and that might be that this is the red giant going back to initial stage that keeps accreting, and then we can have more and more eruptions on top of the white dwarf. So the system recovers really fast after an explosion. So we know this from several novas that we have monitored. So there is an explosion, but the system continues accreting material just like really, really fast. After a few months, it starts piling up and it continues going super nova explosion.
Ron Raddick?
All right, had to get the mute button off there. Nice presentation, Jordi. Thank you. When you were talking early on in the presentation about just the general conditions of a nova, you mentioned the emission of gamma rays and what you called super soft X-rays, which of course represent a couple different photon energies. I'm curious about the mechanism that would create those two photon energies. Is it strictly the heat and the thermonuclear explosion, or something else? And why would those two photon energies be dominant?
That's basically because the temperature on top of the white dwarf is still like really high. And just because of these temperatures, it produces this type of emission. It's just X-rays coming from burning on top of the white dwarf. We don't think it's anything else in that. So there is no other mechanism that triggers this super soft X-ray emission.
Okay, thanks.
High temperatures. Thank you.
Mike Gardner.
Yeah, hi, thank you. I'm curious, I'm not trying to spook this project, but what happens if the star is behind the sun at the time that it decides to show off? What do we do then?
Oh, wow. We'll say that if it's, we wouldn't see it because it would be bright enough, like the sun would just eclipse this. But say that we will need to go to, I'm not sure exactly if that constellation actually goes behind the sun and in what time of the day. Well, that would be during the day, but we wouldn't be able to see it. We will probably need to, we wouldn't be able to see it at this time. Yes.
Hi. So you said towards the beginning or at some point that T Coronae Borealis is got some peculiar features like the pre-eruption dip in brightness and other things. And I'm wondering how many other recurrent novas we know about and if we have any idea why they don't do things like that.
Yeah, the problem we have, that's a great question. So the problem we have is that we have seen many, the typical classical nova scenario, we have monitored many, we have many observations of those, but what we call recurrent novae in our galaxy, in the Milky Way, we only have identified like a dozen, like 11. And among these observations that we have, we don't really see those specific features. It also might be that, this is one recurrent nova that has been monitored for many years, and we have a lot of data collection from many amateur observers, and that's why now we are seeing also these features. I'm just wondering what if we continue observing the other recurrent novae that we have identified, and probably we also see the same features. So it might be that probably we haven't seen them yet, or it might be that it's something very specific from that system. Probably at this point, we don't really have the answer to that, but it might be maybe that's something that happens in other recurrent novae.
So we don't know if it's just a special nova or if we just don't have data on other nova yet.
Exactly. So we don't know yet. So probably need more observations from other recurrent novae and see if these things also happen in the other systems. And probably if that's consistent, if that's common features, maybe we'll probably need to find a good explanation for these specific features. Thank you.
Steve Barr, online.
Okay, yes, my question would be, is there differences in the spectrum just pre-eruption? For instance, as the white dwarf continues to accrete mass from the red giant, one would expect that as it's going to pull more and more hydrogen in, and as a result, I would expect an increase in hydrogen emission lines. Is that a valid assumption?
Yeah, that might be correct. However, I don't have information about the emission lines from this Coronae Borealis, but that might be a possibility. So basically, this is a very massive white dwarf. As soon as you start accreting material, this is ready to explode. And once there is the first explosion, so the system recovers really quickly, like in like a couple of months, and that keeps piling up material on top of the surface. And the temperatures are so high that might trigger probably not like a big explosion, but sustained outflows or a sustained secondary explosion. I don't know how to answer this question because I don't have data for those specific hydrogen lines, or I didn't see any light curves or spectra from this Coronae Borealis. But that would be possible to increase this emission from hydrogen because of these explosions. So that might be something to look at and see if that matches this secondary explosion. So that might be the explanation too.
Yeah, that's something I have been watching, and I haven't seen a noticeable impact at this point.
All right, so that's great. So, so we will probably need to find an explanation for this increase of brightness after the first explosion, if it's not indeed like a secondary explosion or a milder explosion on top of the white dwarf.
Hello, Jordi.
Okay, thank you.
Thanks.
Hello, Jordi. This is Marcus Harper. Thank you for the talk. My question is you kind of alluded to the fact that convection was the primary heat transfer mode in this process. Do you have a sense for what percentage the other heat transfer modes might contribute to it?
Well, so convection in the problem of nova explosion is important because some of the chemical species that you produce during the outburst, like the nitrogens and the fluorine, they get transported to, or they start circulating, and when they go to the uppermost levels, because it's colder, so there are two different ways they can decay, and they choose to decay emitting beta or emitting beta decays instead of continuing proton capture. So that's why when they are there, so it's or they choose this specific decay, and when they decay, they emit all this energy, which creates degeneracy. So that's what the convection actually does in the nova problem. Now, so convection probably is the main means of transport during the explosion. Yes.
Okay, thank you.
Mm-hmm.
Hey, Jordi, Joe Pineda, quick question. You had one slide that had, looked like luminance, you said 0.01 to 1. Is that magnitude 0.01 to 1? Is it going to be that much brighter?
No, that would be the luminosity of the white dwarf, like the intrinsic brightness. All right. So that wouldn't be related to the magnitude because we will need to calculate the brightness according to the distance of the system to Earth. So one thing would be the magnitude, but that would be like the absolute magnitude, not the visual magnitude. Yeah. So the luminosities correspond to intrinsic magnitudes.
Okay. Copy. Thank you.
All right. Thank you.
Any other questions online, in the room?
I think that's it.
Well, that was fascinating. Jordi, we truly appreciate it. And again, thank you so much.
Well, thank you so much for inviting me. All right. Thank you.
Oh, you're welcome. Absolutely.
Thank you.